Another new thing that we can now handle, now that we've learned about linear differential equations, is analyzing some kinds of electrical circuits. And we're basically only going to look at really simple ones. And if you're not familiar with the stuff, don't worry. I'm not extremely familiar with it either. It's definitely not my specialty. And we will sort of explain how the different components work and how they lead to a differential equation. And the main important part that's expected of you is knowing how to get to the differential equation and how to work with it and analyze the problem from there. So every one of these physical systems that we're looking at, anytime you look at a physical system, there's going to be some underlying physical law that you're using to generate the model, to generate the differential equation. So like with Newton's law of cooling, it was Newton's law of cooling, this idea that, the rate at which the temperature tries to equalize will be proportional to the difference between the environment temperature and the object temperature. And then you write that law as a differential equation. With objects subject to forces, you would use Newton's second law. With those chemostat problems, typically it was some conservation law that you write down, like, okay, the amount of this thing should not change. So then you get a differential equation. Rate of change of thing equals rate thing in minus rate thing out. With electrical circuits, there are two laws to focus on. And for now, there's just one until we make them a little bit more complicated. So the physical law that will be used to produce differential equations is Kerkoff's voltage law. Which is actually a kind of conservation law. So it's not necessarily very different from the previous kinds of laws that we've discussed. It's a kind of conservation law because it's about conservation of energy. If you think of voltage as energy, then Kerkoff's voltage law is a way of stating conservation of energy. So here's what the law says. If you add... Okay, so before I state the law, there's something that you need to know about voltage. When you measure voltage in a circuit, you don't just measure it at a point. Like, it doesn't make sense, unless you create a reference point, it doesn't make sense to just draw the circuit and be like, okay, what's the voltage right here? That question doesn't make any sense. When you measure voltage, it's across a pair of points. So like compare here to here. What's the voltage difference between here and here? So it's only differences in voltage that actually matter. What you can imagine is if you've ever used a multimeter, you have two probes, right? And you have to stick both probes, one in one place and one in another place in the circuit, and it'll tell you the voltage difference between two places. So that voltage difference sometimes is called a voltage drop. So, for example, from here to here, there's a certain voltage difference. From here to here. And these voltage differences across the circuit components, like from here to here, from here to here, I'm going to refer to these as voltage drops across the circuit components. So if you add up the voltage drop across each component in a loop, like this here is a loop, you should get 0. And this really is a conservation of energy type statement because voltage is a way of talking about potential energy. So it's sort of like saying, when you look at the voltage drop, you're looking at the potential energy difference from one point to another. Almost. The units are a little bit off. It's potential energy per unit charge. Okay, but you don't necessarily need to understand any of the physics to really be able to use this law just to get to the differential equation. All you need is to know okay, if I add up the voltage drops, then I should get 0. That's an equation. You can write it down, and it'll end up being a differential equation often. Okay, so this by itself is not enough. Each component, you'd have to know what is the voltage drop. And to know the voltage drop, you have to understand how that component works. So for example, what is the voltage drop across this thing? What does the symbol even mean? Okay, so let's talk about each of the components and then write down the voltage law and see how that's a differential equation. All right, so let's go through the components one by one, and I'm going to start with the easiest one. So this one is written either like this, a circle with a function written inside it, and an alternative way to write it is like this. And it just stands for a voltage source. So if you measure across here and here the voltage, you will get as your output whatever is this function. So this has to be given to you somehow. For example, if this is like a AA battery or something, then you would know that it's just 1.5 volts. It's a constant function. It would just be 1.5 constant. So this would have to be given to you in the problem. What function is this? This is the power source for the circuit. So it's a voltage source. Sometimes it's called EMF rather than voltage source. Sometimes it's called the EMF for this component or something like that. Okay, so that one requires the least thinking. Now how about this one? That's a symbol for a resistor, and usually there will be some R next to it, not only telling you it's a resistor, but assigning a variable name, R, to refer to what's called the resistance. So the main question for all of these components is, what is the voltage drop across this thing? So if you measure here to here, what will it be? And the answer is, for a resistor, it depends on the current. So resistors resist the current, resist the flow of charge. So if the current through the circuit is I, then the voltage drop from here to here will be proportional to the current. So that's called Ohm's law. So this will be the voltage drop. You could call that the voltage drop V sub R, the voltage drop across the resistor. So if you measure voltage here and here, then if there's zero current, you're going to measure zero voltage drop. If you ramp up the current, the voltage drop ramps up proportionally. R, the resistance, is the proportionality constant. And this is called Ohm's law. But you don't need to really think about any fancy names. You can just think, the way resistors work is that their voltage drop is given by this. How about capacitors? So that was this symbol. And usually a C is written next to it, not only to help you know that it's a capacitor, but to assign a variable name to what's called the capacitance of the capacitor. So main question, if you measure voltage here and here, if you stick your probes here and there, what is the voltage drop? So a capacitor, physically, it's just two plates with some space between them, or some non-conductive, some other kind of material between them. And so charge can build up on the plates. The plates are conductive, but this space between them is typically not. And charge can build up. And the voltage drop across the capacitor is, let's call it V sub C, is proportional to how much charge has built up on the plates. And the proportionality constant is 1 over C. And we can refer to the charge that's built up on the plates as Q. So Q is usually used for charge. And if this looks a little bit weird, you might rewrite it like this and think, okay, the capacitance, C, is this proportionality constant that tells you how much charge you can get, how many coulombs of charge you can get, maybe, per volt that you put across the capacitor. So what we care about is usually writing it this way, since we're just going to use it in the voltage law. And finally, so going back to the circuit, you've now seen this symbol, this symbol, this symbol, and then this last one, the inductor, is kind of interesting. So it's this squiggle, and there's an L, and that L is telling you a constant called the inductance of the inductor. And what is the voltage drop across the inductor? So let's call it V sub L. So it's going to depend on the current, just like with a resistor it depended on the current. But it's not going to be so simple like Li. So the idea, the reason the symbol looks like this, is that it's something like a coil of wire. I don't know what it is literally. It probably can literally be a coil of wire. And when you run current through a coil of wire, or even just a wire, you generate a magnetic field. When you run current through a coil of wire, you do that even more so. So as you run current through here, you generate a magnetic field, sort of physically around that portion of wire. And generating that magnetic field requires energy. And how strong of a magnetic field you generate depends on how much current you're running through here. Since it requires sort of putting energy in to generate more magnetic field and taking energy away to get rid of the magnetic field, the effect of this is to the effect of the inductor is to sort of resist changes in current. So it's not resisting current like a resistor is, but it resists changes in current. As you try to increase the current, you end up having to increase the strength of this magnetic field, and that takes time. So you experience a sort of resistance. It like sloshes kind of against you. So that's my explanation. I can't say that I fully understand what's going on, but the law that you end up with is that the voltage drop across here is proportional to the rate of change of the current. So di dt if I use I for the current through here. Okay, so we will actually get back to inductors later in the course. For now, let's look at circuits that just have capacitors and resistors. So here was our original circuit diagram, and actually I'm going to go back on what I said. Let's include the inductor for now, just so we can write down a differential equation. So here's Kerkoff's voltage law written up. If you add up the voltage drop across each component, you should get 0. So that means 0 equals, and the voltage drop across this thing was just whatever that function is. That will be something given to you. So it might be a constant if it's just a DC battery. Plus, let's do the resistor. That was Ohm's law. The voltage drop was, well, let me just write them down as variables. Voltage drop across resistor, across capacitor, across inductor. So that means we've got 0 equals E of t plus, and then Ohm's law told us this was resistance times current. And the way capacitors work is that the voltage drop across them is proportional to the charge, and the proportionality constant is 1 over the capacitance. And the way inductors work is that the voltage drop across them is proportional to the time rate of change of the current, with the proportionality constant being the inductance. Oh, by the way, I didn't mention that these all have units. So the voltage, like this, would be measured in volts. Resistance is measured in a unit called ohms. Capacitance is measured in farads. And inductance is measured in henries, I think. Let me look that up. Yeah, that's right. Okay, so back to this. So it sort of looks like a differential equation, but one problem is that we're not being totally clear about what is playing the role of our x of t, our unknown function. So let's try to be more clear about that. And actually, one comment first. I think, so if I were to take this component here and cut it out, and then flip it around, and then paste it back in. So flip it around, and then paste it back into the circuit. Then I would change the polarity in such a way that the voltage difference would become reversed, right? If I subtract voltage here minus voltage here, or however I was measuring it, I would get a minus sign. So if I just take this out and flip it, then I get a minus sign here and here. I think the convention people usually use is such that you do have that minus sign. So let me assume that I have used that convention. And let me write this in sort of a more conventional way, or at least a way that more agrees with what your textbook has, so that there's not so much confusion. So E of t equals this plus this plus this. And again, I have not been so clear about what is my x of t, what is the unknown function. Well, depends. What do you want to know about? What do you want to know about the circuit, right? Do you want to know about the voltage drop across the capacitor? Is that specifically what you happen to be interested in? Do you want to know about, well, I mean, if you do, then here is my equation that governs the capacitor. So if you want to know about the voltage drop across the capacitor, it's this. Ah, but to know this, I must know Q, the charge on the plates. Interesting. Okay, do you want to know the voltage drop across the inductor? Just use this. Ah, but to know this, I must know the time rate of change of the current. Okay, maybe I want to know the voltage drop across the resistor. Ah, but to know that, I need to know the current. So to know various bits of information, I either need to know the current, or the time rate of change of the current, or the charge on the capacitor plates. It seems like the main thing to know about in order to know what's going on in this circuit is those two things, the current through the circuit and the charge on the capacitor plates. But actually, those two things are really one and the same, sort of. They're linked. The way that the capacitor builds up charge on its plates is that charge has to move to the plates, and that movement of charge is current. So there's a relationship between Q and I, which is that the rate at which charge builds up on the capacitor plates is the current. The current is the rate at which charge is moving. So the way current works is you focus on a particular point on the circuit and you say, what's the current through that point? It's the number of coulombs of charge that pass through that point per unit time. That should equal the number of coulombs of charge that pile up on the capacitor per unit time. So ultimately, if we know the function q of t, then we can take its derivative and we know I. And we can take that derivative of that and we know I prime. And then we know everything, right? We've got the I to fill in here and we know about this voltage. We've got the Q to fill in here, we know about this voltage. We've got the di dt to fill in here and we know about this voltage. So ultimately what you want to know is I here, or is Q of t. It would also be good to know I of t because then you can just integrate to get Q of t. So our unknown function, our sort of x of t, let me call it that, our x of t is Q of t or I of t, either one. Either get Q of t and take its derivative to get I of t, or get I of t and take its integral to get Q of t. So let me rewrite this differential equation then. E of t, that's a given function, so that's just some function given to us. R, I, let me write it in a way that favors Q. So instead of I of t, I'll write Q prime. then plus 1 over C Q plus L, and then I prime. Well, I is Q prime, so I prime is Q prime prime. Ah, so it's a second order differential equation. Okay, that's definitely not a kind of differential equation that we have really studied, a second order one like this. We will study this soon, but what we can study for now is the case where L equals 0, so the case where you don't have an inductor. So let me scribble out this inductor, pretend that this is just a straight piece of wire here connecting, and there's no inductor. Then this becomes what we would call an RC circuit, a circuit with a resistor and a capacitor, and a voltage source, possibly. So for an RC circuit, something like this, R, the resistance, C, the capacitance, Kerkoff's voltage law becomes this differential equation. Where the unknown function is Q of t, is the charge on the capacitor plates. So this, I claim, is a linear differential equation. Now here's how you can see that. So I'm going to write the right-hand side on the left side, first of all, and I'm going to divide everything by R. And look at that. We have unknown function of t, Q of t, plus some function which you might call little p of t times Q equals some function which you might call little q of t. And there it is. It's a linear differential equation. So that means you can use the method of integrating factors to solve this. So you can use the method of integrating factors to understand these RC circuits. And you will do that on your homework. For example, in this problem, you've got an RC circuit, so you will basically just work with this equation. Also, in this problem, you're told, it's not drawn out for you, but you're told you've got a resistor and a capacitor, and you're told the resistance and the capacitance. And you're given some initial conditions. And in this one, you've got, why does it look like that? Okay, it's fixed. I'm not sure what happened there, but the minus sign wasn't displaying properly. So you've got this aging battery, and the voltage on the battery depends on time. So this is a function of t. So in this problem, you're sort of being told what is E of t. So you're being told what the right-hand side here will be. So I just also want to mention the way people think about this, or the way engineers think about this. I guess the way a mathematician would think about this maybe is just that it's a differential equation. But I think the way an engineer looks at this is that E of t, this voltage source function of time here, is what they're doing to the system. So it's like, okay, I can control E of t. That's what I impose on the system. And then you think of Q as the way the system responds. So if I do E of t to the system, then how does the system respond? What does it do in response? That's Q of t. It tells you the charge on the capacitor, and if you take its derivative, the current. And typically what you want to do in engineering, I guess, is to figure out what you should do to a system in order to get it to respond in the way that you want it to respond. To figure out how the system responds, to figure out Q of t, you have to solve a differential equation. So that's the idea. All right, and I hope you enjoy those homework problems.